Hi, Sanjay here. So it's come as a surprise for me to realize that everybody seems to have got it wrong. They tuned both the receiver and the transmitter to the same frequency in radio frequency style, expecting the best results. What they didn't realize is it's a complex transformer model. For example, the transmitter has a coupled portion, KLP, and an uncoupled portion, 1 minus KLP. That changes everything. Very briefly, the primary resonant capacitor CP produces one resonant peak at any given moment, but that peak keeps shifting depending upon the load for any given coupling. Unfortunately, if you have another resonant capacitor present, CS in this case, it interacts with the existing inductances to produce one more simultaneous peak, which is also moving with respect to load for a given coupling. So what really happens is you land up with two resonant peaks at any given moment, both of which are moving almost independently and arbitrarily with respect to load. And now add in changes in coupling, and there is no way you can keep track of it with any smart firmware or any equations. In other words, if you really want to optimize, the first step you have to do is to remove this secondary side capacitor, in effect get rid of the false double resonator approach. And that is why, for good reason, we patented the elimination of the secondary side capacitor. We are the only ones who do not fall for the false double resonator approach, realizing its consequences. In other words, elimination of CS is a basic prerequisite to get any smart firmware to work. But in case that was not enough, they introduced another huge mistake: fixed frequency switching, which, as I will show you now, is very detrimental to efficiency. So I'm not going to try and intimidate you with this schematic. The experts will understand. It's simply a full bridge driving an LLCR circuit. In other words, I have eliminated the CS, secondary side resonant capacitor, and yet I'm going to show you fixed frequency operation can be very detrimental to efficiency. If I add CS, it'll make things even worse and even more unpredictable, and I don't even want to go there. So basically, in the schematic, I chose the primary or transmitter side inductance and resonant capacitor in such a way that the resonant frequency with no load, basically based on LC, would give me about 98 kilohertz resonant frequency. And with the load attached, I could show that it would be shifting to 111.5 kilohertz, which, by the way, Chi and all don't understand. And then basically I'm going to go 5% higher than the resonant frequency, which is the inductive side of the curve, and show you that things look quite good. But if I go 5% to the left or below the resonant frequency, things totally fall out of place, which is what happens with fixed frequency operation under certain load and coupling conditions. So this is switching on the inductive side or right side of the resonant peak. So I'm switching at 117 kilohertz, and I'm going to confirm that all the signal generators have been set at 117 kilohertz, and the phase is basically maximum or 180 degrees phase shift between the left half bridge and the right half bridge to give you full power. And now I'm going to simulate it. These are the results. The most important thing you have to look at here is the shape of IQ1, which is the current through the top FET of the left hand side. So I'm going to focus there, and you can see it's quite well behaved. And I'm now going to look at the dead time. That is the time just before the gate of that FET comes on. It's about 200 nanoseconds. And you can see that the current was a little negative at that time, and corresponding to that there was a current in the diode across the same FET. And you will notice that during this dead time the switching node has already gone up, which indicates that the voltage across the upper FET was 0 when it finally turns on here. So that means when it switched, the voltage across the FET was 0, and you had 0 voltage switching, which basically eliminates all switching losses and leads to very high efficiency. So switching on the inductive side unconditionally, irrespective of load and coupling, is what we do always. They don't. With fixed frequency operation, they can land up on the wrong side of the resonant curve, as I'm about to show you. So this time The same circuit exactly is going to be switched at 106 kilohertz, which is 5% lower than the resonant peak. That is called the capacitive side, and I'm going to show you what happens. Just check all the frequencies so you're very clear what we have done, and I'm going to run the simulation now. Once again, look at IQ1, and this time you see huge spikes of current over 160 amperes. And in fact, the only way to see it clearly is to blow it up and make it logarithmic, as I've just done here. And so have a look at the dead time now, which is just before the gate of that upper FET Q1 turns on, 200 nanoseconds prior to that, and there is no current. Last time we had a little negative current, and there is no current through the diode this time, and the switching node is low during the dead time, and it has a crossover at exactly the same moment as the FET turning on. So this is a high switching loss scenario. You're going to get very poor efficiency. And this is what happened with Apple's misguided 127.7 kilohertz version of Qi, and is happening with EV charging at 82 or 85 kilohertz fixed frequency. Now add to that the problem of CS, and it is completely crazy. You cannot even handle it with any software or firmware. And that is why I have been saying their method is doomed. So do you want to live with the dinosaur, or do you want to move ahead? Only at charge edge we understood the importance of eliminating the secondary side capacitor for good reason, and that helped us to enable our secret sauce tracking firmware, so we always switch on the inductive side. Plus we introduced the lowest EMI, zero EMI transmitter structures, a flux laser principle which leads to the lowest receiver side losses, 10 times lower for 10 times more power. Only charge edge understood the complexity of nature, especially resonance, and worked with it, not against it, and it's all proprietary.